NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new.
What if the universe shattered its own laws? The James Webb Space Telescope has unveiled something so bizarre, so utterly impossible, it's shaken the foundations of science. Hidden deep in the Orion Nebula are massive Jupiter-sized rogue planets, wandering in pairs, bound together without a star to anchor them. These cosmic outlaws defy everything we thought we knew, existing where no planet should. This discovery isn't just shocking, it could rewrite the very rules of the cosmos. Stay with us as we uncover the truth behind these impossible worlds, rogue planets and cosmic mysteries. Imagine two giant planets, each as massive as Jupiter, floating through the darkness of space, completely alone, with no star to anchor them. Now picture these two colossal worlds finding each other, locking into a perfect orbit and drifting together in the endless void. How is this even possible? What unseen forces could bind these planets so perfectly? And could there be more of them, hidden in the vastness of the universe? The James Webb Space Telescope has uncovered these strange, impossible objects, hinting at a deeper mystery about how our universe operates, one we are only beginning to unravel. And their story begins with the mysterious world of rogue planets. Rogue planets can form in two ways. Some are born like any other planet within a solar system, condensing out of the gas and dust that surround a young star. But in the chaotic early years of a system's formation, powerful gravitational forces can fling these planets out into the void. Picture a cosmic game of pinball, with planets as the balls and stars as the bumpers, sending these objects hurtling into interstellar space. Others might skip the solar system stage entirely, forming independently in the vast molecular clouds that give birth to stars. This latter process is rare and poorly understood, making rogue planets an alluring mystery for astronomers. The existence of rogue planets was little more than speculation until relatively recently. Advances in detection methods like gravitational microlensing, a technique that observes the brief brightening of a background star when a massive object passes in front of it, confirmed their presence. In 2011, astronomers using microlensing identified 10 Jupiter-sized rogue planets, suggesting that there could be billions of them in our galaxy alone. These discoveries sparked questions about the role these solitary planets might play in the universe. Could they harbor moons with life? Could they act as cosmic messengers, carrying clues about the conditions in their lost star systems? To hunt for rogue planets and other celestial phenomena, scientists turn their telescopes to star-forming regions like the Orion Nebula. Located roughly 1,350 light-years from Earth, the Orion Nebula is a hotbed of stellar creation. It's a chaotic, dynamic environment where gravity battles the intense radiation from newborn stars, shaping the gas and dust into intricate structures. The nebula is teeming with young stars, protoplanetary disks, and vast amounts of material that fuel the birth of planetary systems. It's like a bustling cosmic nursery, and its density makes it a natural laboratory for observing the universe's most dynamic processes. In addition to being visually stunning, the Orion Nebula holds the secrets to understanding how planets form, interact, and sometimes fail to stay in their systems. Rogue planets are just one of the many surprises hidden in this dense and turbulent region. By studying the nebula, astronomers can witness the full life cycle of stars and planets, from their fiery beginnings to the chaotic forces that can scatter them into deep space. It's here, in this celestial arena, that the James Webb Space Telescope made its stunning discovery. Binary systems, where two objects orbit around a common center of gravity, are common among stars. In fact, about a third of all stars in our galaxy exist in binary or multi-star systems. But as you move to smaller objects, such as planets or brown dwarfs, objects too small to sustain nuclear fusion, the likelihood of a binary system plummets. For rogue planets, the odds of finding two of them bound together are astronomically low. Consider this. For two free-floating planets to become gravitationally linked, they would need to be ejected from their original systems at nearly identical speeds and trajectories. A scenario so unlikely it borders on impossible. Yet, against all odds, this is exactly what scientists found. How could such an impossible scenario happen not just once, but dozens of times in a single corner of the galaxy? Is there an unknown force shaping the universe in ways we can't yet comprehend? If jumbos exist, it means the universe is operating on rules we haven't even begun to uncover, and the discovery of these rogue giants is just the first crack in a reality far stranger than we ever imagined. The groundbreaking discovery of jumbos. In a groundbreaking observation that has left scientists reeling, the James Webb Telescope uncovered 40 pairs of Jupiter-sized planets, binary rogue planets, bound together in perfect gravitational harmony, yet completely untethered to any star. This isn't just rare, it's unprecedented. Binary systems like this were thought to be nearly impossible among planets, yet here they are, defying everything we thought we understood about the formation and behavior of celestial objects. How could such a discovery even be real? These newly identified binary rogue planets, now nicknamed Jupiter Mass Binary Objects, or jumbos, are unlike anything previously seen. Each pair consists of two massive planets, roughly the size of Jupiter, orbiting each other without the gravitational anchor of a nearby star. Imagine the sheer improbability of such systems. Two massive objects drifting through interstellar space, their mutual gravity holding them together as they roam the galaxy. This discovery has left astronomers scrambling to understand how such systems could form in the first place and why they are so unexpectedly common in the Orion Nebula. To grasp the scale of this discovery, consider the numbers. Jumbos make up an astonishing 9 to 10% of all free-floating planets observed in the Orion Nebula. This is not an isolated fluke or a statistical anomaly, it's a significant population. Even more striking, the distance between each pair averages about 200 astronomical units. To put that into perspective, that's 200 times the distance between the Earth and the Sun, or about 5 times the span of Pluto's orbit. Despite this vast separation, the gravitational bond between these planet-sized objects is strong enough to keep them in a stable orbit around one another as they drift through the void. The frequency of these binary systems is particularly baffling because it challenges every existing model of planetary dynamics. Binary systems are relatively common among stars, where large gravitational forces can stabilize such pairings. But as the objects involved get smaller, such as planets or brown dwarfs, the odds of a binary configuration drop dramatically. For planets, it's nearly unheard of. The prevailing theories suggest that for two planets to become gravitationally bound as jumbos are, they would need to be ejected from their original systems at almost identical speeds and angles. It's a level of precision that seems impossible given the chaotic forces at play during planetary ejection. So, how did these binary rogue planets form? Recent simulations have provided some clues, but stopped short of delivering definitive answers. One hypothesis suggests that dense star clusters, like the Orion Nebula, may provide the right conditions. In such regions, the gravitational interactions between stars, planets, and gas clouds are extraordinarily intense, creating a kind of cosmic turbulence. In this chaos, it's possible for two massive rogue planets to encounter one another and become gravitationally bound. However, even under these conditions, the high number of jumbos detected remains difficult to explain. What hidden forces or mechanisms could make these improbable systems so abundant? As if the discovery of binary rogue planets weren't perplexing enough, JWST also revealed something even rarer: triplet systems. Among the 40 pairs of jumbos, at least 2 instances of triplet configurations were identified, where 3 rogue planets are gravitationally linked, forming a dynamic system of interdependent orbits. If binary systems like jumbos are improbable, triplet systems are almost beyond comprehension. The complexity of their formation defies every prediction made by existing planetary models. Could these configurations be unique to the Orion Nebula, or might similar systems exist hidden elsewhere in the galaxy, waiting to be discovered? The discovery of jumbos and triplets has implications that extend far beyond the Orion Nebula. It forces us to question the very processes that govern planetary formation and behavior. Rogue planets have long been thought of as cosmic outcasts, formed in isolation or violently ejected from their star systems. Yet the existence of binary and triplet rogue planets suggests there's much more to their story. Are there unknown forces in interstellar space that make such pairings more likely? Or could this phenomenon point to gaps in our understanding of gravitational dynamics? Another intriguing aspect of this discovery is the age of the jumbos. These rogue planets are young, just about 1 million years old, compared to the Earth's 4.5 billion years. This suggests they formed during the turbulent early stages of the Orion Nebula's evolution, a period marked by intense gravitational interactions and rapid star formation. The fact that such systems could emerge so early in their life cycle raises questions about whether they will remain stable over time or eventually drift apart. The discovery of jumbos has sparked a flurry of excitement and debate among astronomers. Some speculate that these systems could offer new insights into the chaotic environments of star-forming regions. Others believe they could serve as natural laboratories for studying the behavior of massive objects in low-gravity environments. Whatever their significance, one thing is clear: the universe still has secrets that defy explanation, and jumbos are among the most puzzling yet. Scientific challenges and theories. What if the universe's most confounding secrets were hidden in plain sight, breaking the rules we thought were unbreakable? That's precisely the challenge posed by the discovery of jumbos. And at the heart of the problem is a concept called the opacity limit, a fundamental barrier in astrophysics that governs how small celestial objects can form. In simple terms, when gas and dust collapse under gravity to form a celestial body, the process generates heat. This heat creates pressure that resists further collapse unless it can be radiated away. But as the object grows denser, it becomes opaque, trapping the heat inside and halting the collapse. This sets a lower limit on the mass of objects that can form directly from interstellar gas and dust. For something to form smaller than a brown dwarf, a failed star at least 15 times the mass of Jupiter, it would need to overcome this natural barrier. The problem? Jumbos fall well below this threshold, making their existence a direct challenge to one of the foundational principles of astrophysics. To explain jumbos, scientists have proposed several competing theories, each intriguing but none fully satisfying. The first is the planetary ejection hypothesis, which suggests that jumbos are rogue planets expelled from their original star systems. This idea is grounded in the chaotic nature of young planetary systems, where gravitational interactions between large planets can send one or more careening into interstellar space. While this mechanism could account for individual rogue planets, it falls apart when applied to binary systems. For two planets to be ejected at the same time, traveling at nearly identical speeds and directions, only to become gravitationally bound in the void of space, the odds are astronomically low. The sheer improbability of this scenario makes it an unlikely explanation for the 40 binary systems observed in the Orion Nebula. The second theory posits that jumbos could form directly in interstellar space, much like stars. In this scenario, small clumps of gas and dust collapse to form massive planets without ever becoming part of a solar system. But here too, physics presents a major hurdle. The opacity limit comes into play again, making it exceedingly difficult for anything smaller than a brown dwarf to form in this way. Additionally, interstellar space lacks the dense, chaotic environments typically required to spark the gravitational collapse needed for star or planet formation. For jumbos to form directly, something extraordinary would need to be at work, something beyond our current understanding of astrophysics. This brings us to a third and more speculative theory, the magnetic field hypothesis. Originally proposed by astrophysicist Alan P. Boss, this idea suggests that interstellar magnetic fields could play a critical role in the formation of smaller objects like jumbos. Magnetic fields could theoretically expel smaller masses of gas and dust from a collapsing cloud, allowing them to form independently, while the rest of the cloud continues to collapse into a star or larger object. While this hypothesis was once purely speculative, the discovery of jumbos lends new weight to the idea. Could interstellar magnetic fields be the missing ingredient that explains how these rogue planets form? If so, it would mark a major breakthrough in our understanding of the forces shaping the cosmos. Recent simulations have added further complexity to the puzzle. In dense star clusters like the Orion Nebula, where stars and planets are packed into relatively small regions of space, gravitational interactions can create conditions favorable for the formation of tight binary systems. These simulations suggest that two rogue planets could become gravitationally bound if they were ejected into a crowded environment where stellar flybys frequently disturb the gravitational equilibrium. A close encounter with a third object, such as a passing star, could stabilize the binary pair, preventing them from drifting apart. But while this scenario makes the existence of jumbos slightly more plausible, it still doesn't fully account for the sheer number of binary systems observed. Why do these conditions seem to produce so many pairs in the Orion Nebula, but not elsewhere? Adding to the intrigue is the discovery of triplet systems among jumbos, 3 massive rogue planets bound together in a gravitational relationship. Triplet systems are vanishingly rare, even among stars, and their existence among rogue planets is almost beyond comprehension. The dynamics of maintaining such a system are so precarious that they shouldn't be possible, yet they are. Triplets add an entirely new dimension to the mystery, raising questions about whether there are additional forces or mechanisms at play that we have yet to uncover. The discovery of jumbos is a humbling reminder of how much we still don't know about the universe. Every theory we have, from planetary ejection to direct formation to magnetic field interactions, leaves unanswered questions and gaps in logic. Are we missing a critical piece of the puzzle, a force or process that operates on scales or conditions we've never studied? The answers are out there, and with tools like the James Webb Space Telescope, we are closer than ever to uncovering them. JWST's role in unveiling the cosmos. For decades, astronomers suspected that rogue planets and other free-floating celestial objects were out there, wandering through the galaxy's dark corners. But finding them was like trying to spot a firefly in a dense forest during a moonless night. Nearly impossible. That is, until the James Webb Space Telescope, or JWST, arrived. With its cutting-edge technology, JWST has shattered the boundaries of what we can observe, unveiling objects and phenomena that have eluded us for centuries. The discovery of jumbos, those mysterious pairs of Jupiter-sized rogue planets, is one of its first and most shocking triumphs. At the heart of JWST's revolutionary capabilities lies its infrared imaging technology. Unlike visible light, which can be scattered or blocked by dust and gas, infrared light can pass through these obstacles, allowing us to see objects hidden in the dense, dusty environments of star-forming regions like the Orion Nebula. This is a game-changer for astronomy. Previous telescopes, including the Hubble Space Telescope, were limited to observing what was visible through less obscured regions of space. JWST, however, operates in the infrared spectrum, effectively lifting the veil on some of the most mysterious corners of the universe. The Orion Nebula, where jumbos were discovered, is one such corner. It's a chaotic, dense cloud of gas and dust where stars and planets are born. Its beauty is rivaled only by its complexity, with intense radiation from newborn stars colliding with turbulent flows of matter. For instruments that rely on visible light, the nebula is a visual maze of glowing gases and dark shadows. JWST, however, cuts through this confusion, revealing objects that were invisible to previous telescopes. Without this capability, the jumbos would have remained hidden, their faint infrared signatures lost in the noise of the nebula. What makes JWST truly remarkable is not just its ability to see through the dust, but also its sensitivity to faint light. Rogue planets like the jumbos emit very little light compared to stars. They don't produce their own light through fusion like stars do. Instead, they rely on the faint heat they retain from their formation or absorb from their surroundings. JWST's infrared detectors are so sensitive that they can detect even this minimal heat, allowing astronomers to identify these free-floating objects in incredible detail. The precision of JWST is akin to spotting a single grain of sand on a vast beach, a feat that seemed unimaginable just a few years ago. Before JWST, our primary method for detecting rogue planets was gravitational microlensing. This technique involves observing the light from a distant star as it briefly brightens when a massive object, like a rogue planet, passes in front of it and bends the light through its gravitational pull. While effective, microlensing is extremely limited. It relies on rare alignments between a rogue planet, a star, and the Earth, and the events are fleeting, lasting only hours or days. Worse, microlensing doesn't allow us to observe the object directly, making it nearly impossible to study its characteristics in detail. JWST changes all of this by providing direct observations of rogue planets, revealing not just their existence but their size, temperature, and even their interactions with other objects. The discovery of jumbos isn't just evidence of JWST's capabilities. It's proof that next-generation telescopes can uncover hidden aspects of the cosmos that we've only theorized about. So what might JWST find next? Scientists are already using the telescope to hunt for more rogue planets, hoping to determine whether jumbos are unique to the Orion Nebula or part of a broader phenomenon. If similar systems are found elsewhere, it could mean that the processes forming jumbos are more universal than we currently believe. JWST's unparalleled sensitivity might even detect smaller rogue planets, perhaps Earth-sized or smaller, drifting through interstellar space. Could these tiny wanderers also exist in pairs? Or are binary systems unique to massive objects like jumbos? Beyond rogue planets, JWST is poised to answer some of the most profound questions in astronomy. It's already being used to study exoplanets, planets orbiting other stars, by analyzing the light passing through their atmospheres. This could reveal the chemical compositions of these atmospheres, providing clues about whether they might support life. JWST is also peering into the early universe, observing some of the first galaxies that formed after the Big Bang. By studying these ancient structures, scientists hope to uncover how galaxies evolve over billions of years. But what truly sets JWST apart is its ability to surprise us. The discovery of jumbos was unexpected, a phenomenon no one predicted or even thought to look for. It's a reminder that the universe is far more complex and mysterious than our current models can explain. JWST has only just begun its mission, and already it has expanded our view of the universe in ways that were unimaginable just a decade ago. If its early discoveries are any indication, we're on the brink of a new era in astronomy, one where the mysteries of the cosmos are just beginning to be revealed. Implications for astrophysics and space exploration. What if these rogue planets are the key to unlocking deeper truths about the universe and our place within it? As incredible as they are confusing, these free-floating binary giants challenge fundamental assumptions about how planets form, interact, and persist in the chaotic environments of space. The implications extend far beyond astrophysics, touching on the possibilities of life beyond Earth, the future of space exploration, and humanity's long-lasting fascination with the cosmos. The discovery of jumbos compels scientists to revisit the core theories of planetary formation. For decades, the dominant models have relied on the idea that planets emerge within the gravitational influence of a star. In this framework, stars act as anchors, stabilizing the disks of gas and dust from which planets coalesce. Rogue planets, especially those bound in binary systems, simply don't fit into this picture. Their existence hints at alternative pathways of formation or ejection, pathways that may be far more common than previously thought. This forces a re-evaluation of not just planetary dynamics, but also the conditions in star-forming regions like the Orion Nebula. Could the gravitational turbulence in such regions create entirely new classes of celestial objects? If so, our understanding of what constitutes a planetary system might need to expand dramatically. These revelations also have profound implications for the study of star-forming regions themselves. Jumbos suggest that the chaotic environments of nebulae, where radiation, gravity, and turbulence compete, may be capable of producing far more diverse and unexpected phenomena than we've accounted for. Scientists now have to consider whether the processes that create jumbos are isolated to dense regions like the Orion Nebula, or if they occur throughout the galaxy, hidden in plain sight. If jumbos are as common as their detection in the nebula suggests, then our models of galactic evolution might need an overhaul. These binary rogue planets could play roles we haven't even begun to understand, influencing the distribution of matter and energy across vast stretches of space. But perhaps the most intriguing question raised by jumbos is whether they could harbor life. On the surface, rogue planets might seem like the last place you'd expect to find habitable conditions. Without a star, they lack the constant energy source that sustains life on Earth. Yet some rogue planets may retain enough internal heat, produced by their formation or radioactive decay in their cores, to maintain subsurface oceans or thick atmospheres. In binary systems like jumbos, the gravitational interaction between the two planets could generate additional heat through tidal forces, further increasing the likelihood of habitable conditions. Consider the possibility of moons orbiting these rogue giants. If a moon had the right combination of distance and atmosphere, it could trap heat and provide a stable environment for life, even in the absence of a star. Similar to how scientists speculate about life under the icy crusts of moons like Europa and Enceladus in our own solar system, the moons of jumbos might serve as refuges for microbial life, or something even more complex. Could jumbo systems be cosmic lifeboats, preserving life in the harshest environments of the galaxy? The idea is speculative, but not outside the realm of possibility. And it's questions like these that make the discovery of jumbos so profoundly exciting. Beyond their scientific significance, jumbos highlight the importance of investing in cutting-edge space technology. The James Webb Space Telescope has already proven its worth by revealing these elusive objects, but its potential extends far beyond the discovery of rogue planets. JWST represents a new era in space exploration, one where we're no longer limited to studying only the brightest or most conspicuous objects in the cosmos. By peering into the infrared spectrum, JWST has opened a window into the hidden universe, enabling us to see through dense clouds of gas and dust to uncover celestial phenomena we never knew existed. The discovery of jumbos also resonates deeply with the public, tapping into humanity's innate curiosity about the unknown. There's something profoundly awe-inspiring about the idea of planets drifting alone in the dark, bound only to each other in an endless gravitational dance. They embody the mystery and wonder that drive us to explore the universe in the first place. In a world where so much of our attention is focused on immediate, earthly concerns, discoveries like jumbos serve as a humbling reminder of the vastness and beauty of the cosmos. They inspire us to dream bigger, to imagine what else might be out there, waiting to be uncovered. Future research and the road ahead. What if jumbos are just the beginning? What if the universe is hiding countless other rogue planets and binary systems, waiting for us to discover them? The shocking revelation of Jupiter-mass binary objects in the Orion Nebula has not only reshaped our understanding of planetary formation, but also opened the door to a future of unprecedented exploration. With the right tools, technologies, and even the help of citizen scientists, we are poised to uncover answers to the many questions raised by these celestial anomalies. One of the most exciting developments on the horizon is NASA's Roman Space Telescope, set to launch in the coming years. Unlike the James Webb Space Telescope, which specializes in detailed observations of specific regions, the Roman telescope will have a much wider field of view. This capability makes it an ideal tool for conducting large-scale surveys of the sky, potentially uncovering hundreds or even thousands of rogue planets. Roman will use a technique known as microlensing, where the gravitational field of a rogue planet bends and magnifies the light of a distant star as it passes in front of it. While JWST revealed jumbos by directly detecting their faint infrared light, Roman's ability to observe microlensing events on a massive scale will complement JWST's discoveries, giving us a broader picture of how common rogue planets are across the galaxy. But telescopes alone won't solve the mystery of jumbos. To fully understand these objects, we need to combine observational data with advanced simulations. This is where artificial intelligence is becoming an invaluable tool. AI can analyze vast datasets from telescopes like JWST and Roman, identifying patterns and anomalies far faster than human researchers. For example, an AI algorithm could sift through thousands of microlensing events, flagging those that might indicate the presence of binary rogue planets. Similarly, AI-driven simulations can recreate the chaotic conditions of star-forming regions like the Orion Nebula, testing different scenarios to see how jumbos might form and survive in such environments. As we continue to explore, the tools we develop will become even more sophisticated. Future telescopes might be capable of directly imaging the atmospheres of rogue planets, revealing their compositions and even the potential for habitability. Advances in AI could uncover patterns in astronomical data that no human could detect, offering new insights into the dynamics of star-forming regions. And as citizen science projects grow in scale and scope, the collective curiosity of people around the world will drive discovery in ways we can't yet imagine. As we stand on the brink of a new era in astronomy, it's clear that the universe still has countless secrets to reveal, and the search is only just beginning. What will we find next? The answer is waiting out there, among the stars. Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video for more exciting content.